Yeah, there's also abundant numbers. And these are going to be numbers for which the sum of the proper divisors is more than the number itself. And we just so happen to have an example there. We talked about 12. Well, the proper divisors of 12 were the 1, 2, 3, 4, and 6. And if you add 1, 2, 3, 4, and 6, we got the 16. Yeah, comparison-wise, the proper divisors add up to be more than the number itself, right? That's abundant. Okay? It's abundant. So if this proper divisors equal the number itself, it's perfect. If the proper divisors are more than the number itself, it's abundant. Well, what else could happen? You could have the proper divisors less, couldn't you? Less than the number itself. That could happen too. That's called deficient. Deficient numbers are numbers for which the sum of the proper divisors is less than the number itself. Yeah. So that covers every possibility. Equal, greater, or less. All right. So deficient are the numbers for which the sum of the proper divisors is less than the number itself. All right, let's see. A good example. Well, good example. How about 15? 15. The proper divisors of 15 are, just a few of them, 1, 3, 5. That's it, isn't it? 1 plus 3 plus 5, that gives me 9. So that sum is less than the number. That's deficient. $15 is deficient. Now, I picked 15, but there's actually, if you think about it, there's a group of numbers that we could pick out that would be always less than, that would always be deficient. Can you think of what group I'm talking about? What group of numbers would always be deficient ones? Prime numbers. Wouldn't prime numbers always have to be deficient? Because for prime numbers, you only have 2 factors. And if we're talking proper divisors, that gets rid of one of them, doesn't it? Yeah. What's the proper divisor of any prime number? The only proper divisor of any prime number is 1. Yeah. And so it's always going to be deficient. A prime number is. So anyway. All prime numbers are deficient, yes. All prime numbers would have to be deficient. That is right. Okay. Now, let me go back here to one couple of things. since we talked about Mersenne primes and perfect numbers, let me give you another interesting little fact. There's actually a link between, you can link Mersenne primes to the perfect numbers, which seemingly don't even go together, but all right. If two to the nth power minus 1 is prime, that's a Mersenne prime, right? 2 to the n minus 1, that was our Mersenne prime format. If that's prime, then turns out this combination here, if you go 2 to the n minus 1, same number, times, though, 2 to the n minus 1 power. If you multiply those two numbers together, all right, that's perfect number. Strange, but it does work. 2 to the n minus 1, that's prime. Then 2 to the n minus 1 times, now, what's the difference between this number and this number, the one in the parentheses to the left and the one in the parentheses to the right? The difference is when I subtract the 1, right? Here I do 2 to the n, then I subtract 1. Here I subtract 1, and then I do 2 to that power. You see? Okay, so that's like, let me show you. All right, so we know 2 to the second minus 1, that's prime, right? That's 3. So by this, then, this would say, then I would take 2 to the n minus 1 times 2, and then, of course, the n here is 2, right? So this would be 2 minus 1. Let's see what that gives us. That's 4 minus 1. Of course, that's 3. Times, that's 2 to the 1. That's 3 times 2. Right? What is 3 times 2? 6. Which is perfect. How about that? Let's see if it works for the next one. All right, what's the next one that's prime this way? 2 to the third minus 1, which is 8 minus 1, which is 7. That's prime. All right, so what would this perfect part be? Well, it would be 2 to the third minus 1 times 2 to the 3 minus 1. What is that going to give me? Well, 2 to the third minus 1 is 8 minus 1. And then that's going to be 2 squared. So that's going to be 7 times 2 squared, which is 4, which is 28. 28 is, what's 28? Is it perfect? Yep. That was the second perfect number. The first Mersenne prime gave us the first perfect number. The second Mersenne prime was 7, and it gave us the second perfect number. Well, let's see if it works. I told you that the third Mersenne prime was 496. Let's see if it worked. All right. So the third Mersenne prime, remember we had to go to 2 to the fifth minus 1 to get the third Mersenne prime. That's 32 minus 1, that's 31. Okay? So then we go 2 to the fifth minus 1 times 2 to the 5 minus 1, right? Which would be 32 minus 1. First would be. And this would be 2 to the fourth. So that's going to be 31 times 2 to the fourth is 16. What does 31 times 16 give you? Somebody punch it up. 496. There you go. The third perfect number. Okay, so anyway, it is a link there. Mersenne prime gives you a perfect number as well. So if you find a Mersenne prime, you find a perfect number. Now the other thing I was going to mention on the Mersenne primes, this business of Mersenne primes is a pretty big deal even these days, because prime numbers are very, very nice. You know, they don't factor, so they're hard to determine. But anyway, what I'm trying to get at is they're used in security codes and things like that, in codes. Perfect numbers are always good to have. Prime numbers are good to have. So there's always larger and larger prime numbers. They're always on the search for those. They found some pretty big prime numbers. You know, the list of prime numbers is infinite, but you still have to determine if a number is prime. So the search for these primes is ongoing. The one I have down here, this was from May 2004, and there's been lots found since. Okay, in May 2004, it was found out that 2 to the 24,036,583 power minus 1 was found to be prime. Well, that's what I was going to point out. This would not be possible to put in on your calculator because it has over 7 million digits. And most calculators have, what, 10, 12 digits possible? Yeah, this is, you have to do this with a computer. But there's over 7 million digits for that number. If we tried to say, well, 2 to the 5th is minus 1 is 31. If we tried to say that, well, that's this, we couldn't do it on our very own here. We'd have to.
Someone is trying to prove the point.
Huh?
Figured this out.
Yeah, like I said, prime numbers, it's always good to have more and more prime numbers, and so they're always searching for them. It's actually, it's an internet Mersenne prime search or something like that. But anyway, that was May 2004, and this is 2012, so it's been bettered since. But anyway, what I was going to say then, knowing that one to be prime, what would be the perfect number there associated with that? Well, we can't get the actual number out of it, but we can put it in this form right here, couldn't we? It'd be 2 to that minus 1, 2 to the 24,036,583 minus 1, times 2, what would be the other one? Well, it would be that power minus 1, wouldn't it? So it'd be 24,036,582. See that? That would be a perfect number, because it's always, you find one, you find the other. See what I'm saying? I just changed this to 1 less power, and that's going to be a perfect number. So anyway, lots of interesting little facts and things that are going on that maybe we know nothing about, but now we know a little bit about. Okay. All right, one other last thing, and that is tell you about Goldbach's conjecture. Goldbach's conjecture goes like this. Every even number greater than 2 can be written as a sum of 2 primes in at least one way. Meaning there could be more than one way, but at least one way you can do it. All right, so for example, 12. I can write 12 5 plus 7, couldn't I? So there's a way to do that one. Okay? What about 20? Could I write 20 as 2 primes? Think of one. Sum of 2 primes. 13 and 7? 7 and 13? Sure could. Okay? So we can do that for every even number. Now, yeah, 20 is a good one too. Is there another way I could do 20 with 2 primes? 17 and 3, yeah. So, we could do that with every one of them, but it could be possible that we could do it more than one way. So, but Goldbach's conjecture says there's at least one way to do it. Now, what you want to be careful with is, let's see, if I was doing 24, could I do that with how about I can't think of going 3 and 21? Well, 3 and 21 is 24, but what's wrong with that? That's not right. Doesn't show Goldbach's conjecture because we're talking 2 primes. Is 21 prime? Yeah, just be careful when you're doing these, because what they'll do is they'll say verify Goldbach's conjecture for such and such a number. Be sure you get 2 primes there. How could I do it better there? 19 and 5, okay. 17 and 7. 3 and 21 doesn't. But yeah, just be sure you get 2 prime numbers there. Now, the other thing, what about 4? How can I do this for 4? Because it says every even number greater than 2, and 4 is greater than 2. How can I do it for 4? 1 and 3? Not 1 and 3, why not? What about 1? Is it prime? We talked about that last time. 1 is not prime, it's not composite, it's neither one. So it wouldn't verify Goldbach. Now this one we'd have to use 2 of the same, wouldn't we? 2 and 2? Yeah, it doesn't say it has to be 2 different primes. So you could do 4 with 2 and 2. Just like you could do 10 with 5 and 5. You could do it 3 and 7 too. But anyway, all right? So anyway, just a few little interesting